Okay, let's start. Good morning. Welcome back. I hope you had a nice break. I certainly did. It was pleasant. So, we have been discussing the mean value theorem. So we're going to discuss two different versions. This is mean value theorem 1. And as you can see here, this is for paths. So the input space is one-dimensional. And then we're going to upgrade this to arbitrary C1 functions between open sets of norms, open sets of norm spaces. Now, in 1D, in 3210, you've also discussed one version of the mean value theorem. But remember there, you had an equality. Okay? Now, in the higher dimensional setting, you have an inequality. And in the last problem set 2, you're going to be looking into situations like this. Where can you come up with an equality and so on? And so this mean value theorem as an inequality, it turns out that it is one of the fundamental inequalities. So just to remember, we had a couple of important inequalities that we discussed so far. We said, for instance, if we have an inner product space, what is the inequality that is like very fundamental? We're going to get there, but with the case of an inner product space, we have something more sophisticated. If you have a dot product, what can you do with that?
Define orthogonality.
Yes, but I want the inequality.
It's the like Bunyakovsky inequality.
Yeah. Just to recap. If there's an inner product, then we have CBS, which says that if I were to take two vectors v and w and take their inner product, now this is a number. Well, this number is bounded in absolute value from above by the product of the norms. Do we remember this? This is the fundamental inequality when you have an inner product. And like your friend suggested, if you have a metric, not necessarily an inner product or just a metric, or if you have a norm, then you have the triangular inequality. And you have Ti. And what does that say? Well, in terms of metrics, let's write it in both ways. Triangular inequality in terms of metrics says the following. The distance between x and y, between two different points x and y, is dominated by the sum of the distances from x to some other point z plus z to y. This is triangular inequality if you're using the metric. In terms of the norms, it takes the following form. So you can say x plus y in norm is bounded by x in norm plus y in norm. These look slightly different, but they are equivalent statements, really. Okay. Now, what I'm saying here is that mean value theorem is, again, a fundamental or foundational inequality as important as these. It takes a while to prove it, as opposed to these things. But still, it's very important. And while we're here, because I'm going to use it in the proof of this, you also had reverse triangular inequality. Do we remember this? Okay, let's write that as well. And so what was the point of the reverse triangular inequality? Instead of upper bounding this term, you want a lower bound using the differences. Now, I hadn't written it using the norms, so let's just use it. Let's just write it using the norms. It just says that x minus y in norm is bounded from below by x in norm minus y in norm, all in absolute value. Okay. Now, of course, I'm not writing the details here, but when I write it like this, you should look into the types of these objects. So here, x and y are vectors, right? I'm taking their difference. So this thing, again, is a vector. And when I put this absolute value stuff, it really means the norm. Okay, vector, and then norm, so that the right-hand side becomes a number. Now, on the left-hand side, again, I have x, the vector, y, the vector. When I put the absolute values next to the, or between, or around the vector, now this is the norm. So I'm saying the norm of x minus the norm of y. And then this outer outer norm is really the absolute value, because this is a number, this is a number. I'm taking the absolute value of their difference. Do we remember things like this? Okay. Okay. Now, I had given you one proof of this, assuming a statement about lengths of differentiable paths. And in the latest problem set, you're going to see, or you probably have seen by now, that did become a problem. So let me remind you. Proof 1 was using the fact that the length of the path gamma from lambda to rho is nothing but the integral of its speed. So look at gamma prime of t. Now this is a vector. Take its norm and then integrate. I'm not going to write how to actually turn this statement into a proof of this. The point is that once you have this, well, the left-hand side is dominated by the length. But then this, well, this is dominated by the length of this interval over which you're integrating times the max of the integrand, which is exactly the right-hand side. That's how we proved. I want to give another proof using essentially the definitions. Part of it is that this second proof, in fact, works more generally. And I will give it as an exercise to write down the proof adapted so that it works for a more general situation also. So first, let me call this number k. Now let's remember, gamma being C1 meant that it is a continuously differentiable path, taking values in n. So it is differentiable. Gamma prime exists for each t. And furthermore, it is a function of t, and that is a continuous function. gamma prime of t is a continuous function of t. And certainly, when I take the absolute value to, or norm 2, this thing itself is a continuous function. And I'm taking the sup of it over a closed and bounded interval. By the maximum principle, this thing attains its max, meaning that instead of the sup, I could, if I wanted, write max, and it is guaranteed that this number is a finite number. Okay. Call k to be this maximum speed. And recall this is how we interpreted this number here. So I look at the statement I'm trying to prove. It's this inequality. And before we had the break, I drew this picture. Should I draw that picture again, in case some of you weren't in class, to give you an idea? Yeah, so where should I do this? Let me write it here. Okay, so here is the reals. Here's an open interval. Okay, this is my I. Here is n. It's an open subset. Maybe it has multiple components, but I don't really care about that. It's a subset in this normed space F. Then I take 2 points, lambda and rho. Let's call this positive infinity. So lambda is to the left of rho. Oh, even before that, let me just write. I have a function, gamma, that takes this open set to this open set. Okay? So now, I fix 2 points, 2 time parameters. One of them is lambda, the other one is rho. And I really look at the image of this closed and bounded segment under gamma. Okay? At time lambda, gamma is somewhere. Let's call it maybe like this. And as I increase the time from lambda to rho, while gamma of t draws a certain path in n, and when time is rho, it stops at some other point. Okay. And it does so in a differentiable manner. Okay. So maybe this is what it does. Okay. So what is the left-hand side? The left-hand side is this, the difference between the endpoints. That is to say, it's the length of the line segment that connects the beginning point and the end point. Okay? Now, in this situation, I drew n, this target open set, this way, just to clarify this. I don't really need this line segment to be completely in n. Okay? Maybe the line segment is, maybe it's not completely inside n. That's not a problem, because I'm not really looking at this line segment. I'm just looking at its length. So this is the left-hand side. What is the right-hand side? Well, certainly, this factor is nothing but the length of this blue interval. Okay? And what is this? Well, this is the maximum speed. And how do I think that? Well, I say the following. Let's say I have a typical time t here. At time t, gamma is here, let's say. This is gamma of t. And then I interpret gamma prime of t to be the velocity, right? It's a vector. It tells me where gamma is moving at time t. This tells you the position. So gamma tells you the position. Gamma prime tells you the velocity. So I imagine gamma prime of t to be a vector tethered to this particular point, gamma of t. Okay? So gamma prime of t is something that has both magnitude information and direction information. Right? So when you're talking about velocity, it tells you where you're going. When I take the norm of this vector, I get rid of the direction information, and all I'm left with is the magnitude. Well, the magnitude of velocity is speed. Okay? As t goes from lambda to rho, okay, like this, gamma of t moves from here to here. And to each point, imagine the velocity vector sort of tracking the position. At each of these points, instead of looking at the velocity, I look at the speed, just the magnitude, so that that's a number now. And I look at the max speed this way. Okay? Because maybe, in principle, this path is slowing down at certain times and speeding up at some other times. Right? So this is not telling you anything about the space-time. Does this make sense? So this is the intuition. Okay. And so given this more, let's say, dynamical perspective, what I'm going to do is this. I'm going to look at, instead of the whole segment, I'm going to look at smaller segments. Okay? Let's say I'm going to go from lambda to not rho necessarily, but up to some time t. That is to say, I'm going to take this expression, and I'm going to take it to be variable in this entry. Okay? So based on this, let me define the following set. For epsilon positive, define, let's say, t sub epsilon to be the set of all those times such that, remember this is now k, distance between gamma of t and gamma of lambda, so how much you have moved at time t, being bounded from above by the change in the input times k plus epsilon. I'm going to give myself some room. Okay. So this is a set of times. It's a subset of lambda to rho that depends on the parameter epsilon. And so what do I need? What am I trying to show? If I can show that for any epsilon, rho is in t sub epsilon, I would be done. So somehow we're going to have to do some stuff to figure out that for any epsilon, rho is indeed in this set. Let's think about what that means, what it means for a rho to be in this set. Rho is in T sub epsilon if and only if this bound I want to get works up to an epsilon. But what I'm saying, if that works for arbitrary epsilon, then I can optimize over epsilons and get the actual bound I need. Okay, that's the idea. So first, let's think about this set. For fixed epsilon, is the set empty or non-empty? Yeah, for instance, what is there? Give me a point, give me a time that is in there. Lambda is there, right? So if t were lambda, gamma of lambda, this is just 0. So the left-hand side is 0, there's nothing to do. So this is a non-empty set. The initial time is in my t sub epsilon for any epsilon. I'm going to leave it to you to verify that indeed this set is compact. So any sequence here has a convergent subsequence. Compact, okay. So compact sets are bounded enclosed, which means that their sup exists and is a point, right? It is included. Hence, max T sub epsilon exists. But then note that any time in T sub epsilon is upper bounded by rho. And so this max of T sub epsilon is upper bounded by rho. I claim that this max is in fact equal to rho. Okay. Any questions so far? Now we're going to have to do something to get this claim. And in moments like this, what you could do is to go back to the statement and see what you haven't used so far. Well, we haven't used the fact that gamma is differentiable. And so we're going to have to use that now. OK. Now we have established that T sub epsilon is non-empty. Let me take an arbitrary point T in it. Okay. I know that my path gamma is continuously differentiable. In particular, it is differentiable at T. Hence, well, what I can say is the following. Using the epsilon delta to open up the definition of the limit that defines differentiability, there is a delta such that for any h, if h is bounded by delta in absolute value, then gamma of t plus h minus gamma of t divided by h minus gamma prime of t in norm is bounded by epsilon. Okay? I just use the definition of differentiability. And how do I get to write it this way instead of gamma prime of t applied to h divided by h and so on? Well, in this case, the input space is one-dimensional, so h itself is a scalar, so I get to distribute it like this. And so now, basically, I want to say something about this using something about this. Well, the way to do this is to use the so-called reverse triangular inequality, like we discussed, to sort of get some bounds. By reverse triangular inequality, this upper bounds this. Okay. And so you see, I have here the norm of the difference of two vectors. Reverse triangular inequality precisely says that this norm upper bounds the distance between the individual norms. That is to say, this is upper bounded by, or is lower bounded by this. Minus this and absolute value. Okay. Why is this nice? Because now this thing is a number, this thing is a number, and here I have absolute values. And so I can get rid of these absolute values to really do something about these numbers. And so how do I get rid of the absolute values? Well, one thing I can say, and this is the part that I'm going to use, is that the absolute value of any number upper bounds the number itself. So if I were to get rid of these absolute values, the quantity could only decrease. Okay. Now this means that if I were to take this to the other side, I have an upper bound on this guy. Okay, this is this term is less than or equal to epsilon plus this. Any questions so far? Okay. Well, by definition, this term is upper bounded by k. Okay. And then in fact, what I can do is I can take the scalar to the other side as well to get something perhaps slightly more convenient to write. Namely this. This is bounded by epsilon plus k times h in absolute value. So k plus epsilon times h in absolute value. Okay. In nothing we did so far, I use the fact that t is in this nice set of times, t sub epsilon. And so if I were to use that, I have the following then. By the triangular inequality, this is bounded from above by this. I know that this is bounded by k plus epsilon times h in absolute value. And I know that this is bounded by epsilon times the difference between these, because I had taken t to be in t sub epsilon. What is it? So k plus epsilon times the difference between the inputs. The point being is that if I were to take h to be a positive number, and for h positive, this s minus this in norm. Well, now this is just h. And then I can collect these two terms. And then here I would have t plus h minus lambda. Meaning, just to summarize all this, if t is in this nice set of times, then for h small enough, t plus h2 is in the same set. Okay. So this is a common method. It's a couple of common methods. First, what did we do? We first had an inequality to prove. Instead of going for the inequality itself, we gave ourselves some room by taking some arbitrary epsilon. We said, OK, let's let epsilon to be positive, and then let me weaken the inequality by adding some epsilon somewhere, and then prove that inequality. That was the first step. Then, based on that inequality, we deduced that there's a certain set of times that is important. This was the set t sub epsilon. I'm going to write its definition again because it's somewhat convoluted, and I think that you might have forgotten how it was defined. We showed that this t sub epsilon, this set of nice times, is non-empty, and in fact it is compact, so its max exists. Then we came up with the fact that if you have a time in t sub epsilon, then there is a time that is after it, t plus h2, that is still in t sub epsilon. So you can take a good time and continue just a little bit. That's what we showed so far. Now let me remind you, there's t sub epsilon. T sub epsilon was a set of times such that the inequality I wanted held up to an epsilon. That's how I think about it. Such that minus lambda. This was by definition. We showed that for any t, there is a delta such that for any h between 0 and delta, t plus h2 is in t sub epsilon. For any h between 0 and delta, t plus h is also in t sub epsilon. So if t is a good time, so is t plus h for some small h. Okay? But then you see, because of the compactness of t sub epsilon, max of t sub epsilon is a time in t sub epsilon. And unless it is rho, I should be able to increase that time by some small h while still staying in t sub epsilon. That's why max have to be rho. Let me write it. Maybe you can write it like so. Suppose the max of t sub epsilon is strictly less than rho. It cannot be greater because t sub epsilon is a subset of lambda rho. It cannot be greater. So possibly this max is strictly less. So let's call that T0. But then by this statement, there is some small h such that T0 plus h2 is in t sub epsilon. Then by, let's say, star, and this is a star, there is an h such that T0 plus h is in t sub epsilon. Well, this is a contradiction because we started with the max of t sub epsilon to begin with. So there couldn't be a number that is larger than the max inside the set. So that's a contradiction. Where is the contradiction? It's here, which means that the max have to be rho. If the max is equal to rho, definitely rho is inside, which means that for t equals rho, this inequality is satisfied. But then it is satisfied for any epsilon, which means that if I were to optimize over epsilons, I get the inequality I need. Okay? I'm not going to write this part. The statement, the proof is somewhat involved, but it's a very simple idea. Writing it down takes a while. Compared to, for instance, Cauchy-Bunyakovsky-Schwarz, but now you have it. Okay. Questions? Okay, so what does it say? What does mean value theorem for paths say? If you're moving in space, okay, let's say from time 0 to time 1, while the total displacement in magnitude should be bounded by the maximum speed. That's what it says from using physical terms. Okay, so here's a nice exercise. In fact, we didn't need gamma to be C1 here. For the first proof, we needed it. But for the second proof, we don't need this. But you're going to have to adjust some of the formalism, just a little bit. So let me state it here. Proof 2 works for gamma. Let me write it like this. Continuous, defined on a closed and bounded interval, such that gamma prime of t exists between, for any t strictly between lambda and rho, gamma prime of t exists. And it's bounded. You're going to have to adjust the proof that we did just a little bit. And I think this would be a very nice exercise, good opportunity to go through the proof again and perhaps write it in your own words. But that's that. Questions? Comments? Now, this was the mean value theorem for paths. We would like to have a mean value theorem for functions between open subsets in arbitrary norm spaces. But the condition, there's a certain condition that has to be satisfied always. Namely, that in the multivariable setting, you're going to have an inequality. And furthermore, you get to do it insofar as you can connect the two input points using a line segment. And here's what I mean by this. So let me let now f to be a C1 function. Again, if I want, I can just stick to differentiable following from this exercise. But the point of C1 is that it's easier to state. And I want the derivatives to be bounded and so on. So it's nicer to use. Now recall, M and N were open subsets in norm spaces, M in E and N in F. Let F be C1 from M to N. And let me let X and Y to be 2 points in the input space. If the line segment connecting these two vectors, these 2 points, is in M completely, then you have basically the same statement. If for any, let's say, tau between 0 and 1, so what am I going to do? I have two vectors. I'm going to linearly interpolate. Okay, lerp is what it's called. Let me denote this by L sub xy of tau, which is 1 minus tau x plus tau y is in M. Then again, the distance between the two outputs is upper bounded by the sup of f prime at this midpoint as tau varies between 0 and 1. Yeah. Let's write it like so. Whoop. And then distance between x and y. Now, just to give you an idea, this is a picture you should have in mind. In the input space, or maybe I should draw it here. In the input space, the line segment connecting x and y has to be contained completely in M. But that is not the case for the output space. In the output space, the line segment could escape the space, escape the set. Okay. If x and y were here, I can apply, because the line segment is completely inside. Okay. But if I were to take these 2 points, then I cannot apply this mean value theorem. The line segment has to be completely inside the input space. This doesn't apply. To this, it applies. Okay? Okay, we're out of time. Well, we're not, but let me just finish. I don't want to start the proof. It's not very complicated now that we have mean value theorem 1, but we're going to continue talking about this tomorrow. Thank you. Okay, let's start. Good morning. Today we're going to start and finish the proof of the second mean value theorem. Remember, yesterday we discussed mean value theorem 1, which was for paths in arbitrary open subsets in norm spaces. That was the sort of more complicated proof. Once we have that, really this is not that complicated. After we discuss the proof of this and some of the perhaps restatement of this that is slightly more convenient, we're going to look into some of the consequences of mean value theorem. Before I start, are there any questions? Now, I should also mention, one of your colleagues at the end of last class asked me about where we are in the textbook. So if you look at the syllabus, this week is reserved for 9.6 and 7 and 9.5. So we're behind, okay? And furthermore, probably I'm going to be skipping a bunch of these optimization stuff first derivative test, second derivative test, all these things, because I want to move on. And even with this reduction, we might end up needing to take the next week as well. That was originally reserved for integral calculus, to the discussion for the inverse function theorem and the implicit function theorem. These are also very important statements. Another thing too, in the textbook, the ordering of the topics is rather different. So for instance, to say the least, in the textbook, they don't cover mean value theorem that for vector valued functions. They have a mean value theorem that for multivariable functions that take scalar values, but that is not the right mean value theorem, in my opinion, to have in mind in multivariable calculus. And furthermore, they deduce mean value theorem out of Taylor approximation, which is kind of backwards, because Taylor approximation is supposed to be something related to higher order derivatives, whereas mean value theorem is only about the first order derivative. Okay? And indeed, you prove Taylor approximation by basically using mean value theorem many times, by induction basically, induction on the number of derivatives. Another thing is that, for instance, very early on in the chapter for differential calculus, they proved this idea that if you have, let's say, if you have a function that is twice differentiable, then the mixed partials commute. That is to say, if you have a function f that depends on two variables, x and y, let's say real variables, and let's say that this is C2, twice continuously differentiable, then this, right, first differentiate with respect to y, then with respect to x, is the same thing as first differentiating with respect to x and then with respect to y. Right, it shouldn't matter in which order you're differentiating. So they proved this very early on, but again, it's kind of backwards because they prove it only for scalar functions, not vector valued functions, but this applies in general. And really the proof of this uses mean value theorem. Remember, I told you yesterday that mean value theorem is one of those fundamental inequalities in differential calculus. And so this was the main thing. So this is the main thing that we're going to use to prove a bunch of things. Okay. So this is so there's a reason why the order of topics is somewhat the other way around. Okay. So how do you prove this? Well, we have a statement for paths. Essentially, I'm going to come up with a path and apply mean value theorem to that path. So for instance, consider gamma takes a t and sends it, well, f of this vector. So 1 minus t x plus ty. It's a composition. Okay? T is supposed to be a real variable. Now let's note that when t is 0, right, gamma of 0 is f of, this is just 1 times x plus 0, so this is just f of x. So this path at time 0 is at f of x. Okay? And at time 1, likewise, so when t is 1, this is 0 and this is 1. So at time 1, my path is at f of y. Now furthermore, gamma is a C1 path, right? Because I can apply the chain rule to this to come up with the derivative. So now I need to differentiate this expression with respect to t. This is equal to the derivative of the outer one evaluated at this point. Times the derivative of the inner thing, right? And what is the derivative of the inner thing? Minus x plus y. That is to say, y minus x. Okay. Now we have developed all this machinery of norm spaces and so on, so that things like this work the way you expect. Okay. Now when you think about this, you see x and y are, well, there are points in M. In particular, there are points in E. F prime, when you feed to it a vector, and this certainly is a vector, now is an operator from E to F. So if you take this vector in E and apply this operator that goes from E to F, ultimately you're going to end up in F, which is what we wanted. Does this make sense? So I developed all this machinery of norm spaces, vector, metric spaces, and so on, so that with minimal sort of adjustment, we can pretty much pretend that everything is single variable, at least formally speaking. Okay. And furthermore, note that f is C1. It is continuously differentiable, which means that f prime is C0. When you differentiate, you reduce the differentiability by 1. So it is continuous. And the inner thing, too, is a continuous function of t. So this is a continuous function of t in total. That is to say, gamma prime is a continuous function of t. That is to say, gamma is C1. So it's a continuous differentiable path. Does this make sense? Another thing, too, is that certainly at 0 and 1, gamma is defined. And in fact, for some epsilon, it is defined at minus epsilon, and it is defined at 1 plus epsilon, because, well, this vector inside is supposed to be a vector in M. And because M is open, any sufficient or small perturbation of x, likewise y, is still going to be in M. And so I can write it like so. For some open interval I containing 0 and 1. Any questions about this so far? Are you happy? No?
Why was it important that you used gamma of 0 and gamma of 1? Like, where did you use that? Gamma of 0.
I haven't used it so far.
Oh, okay.
Fair enough, yes. Where am I going to use it? I'm going to use it here. I'm going to say on the left-hand side is the difference between gamma 0 and gamma 1. Okay. Then the distance between f of x and f of y, well, is the same thing as distance between gamma of 0 and gamma of 1. Now, to this gamma, I can apply mean value theorem 1 to upper bound this. So this is mean value theorem 1. What does it say? It is bounded by sup of gamma prime of t in norm, where t varies between 0 and 1, between the endpoints, times nothing else, because 1 minus 0 is 1. Okay, but then what is this? Gamma prime of t is nothing but this vector. So maybe I should be explicit here. So this is sup over 0, 1 of the norm of this vector. It's a vector in F. Applied to x minus y. What is the last step? In the inequality here, I have this. How do I go from here to there?
Why is it x minus y?
Well, because it's the norm. Fair enough. It doesn't matter. It's the same thing. We're here. We want this. Clearly, they're not the same expression.
Is that less than or equal to the norm of the first times the norm of the second?
Yeah, right. Right. So if you have an operator applied to a vector, if you take the norm, this norm is upper bounded by the operator norm of this times the norm of this. But then the norm of this is independent of t, so we can take it out. Let me just say right-hand side. That's how you prove. So here we use this idea that AV in norm is upper bounded by A norm, V norm. Like the 5th time we're using this. It's almost like I knew that we were going to use it. Okay. Any questions about this? Now, writing this, and even this assumption that you want two vectors such that the line segment connecting them is completely within your open set M. This is kind of cumbersome to write. This is kind of cumbersome to write. Often people sort of like don't write it like this and instead assume further things on M. So for instance, what you can say is that, okay, I'm just going to restrict my function to an open ball. Open balls satisfy this property. No matter which 2 points you choose in an open ball, the line segment connecting the two vectors is going to be completely inside that open ball. This is what is called convexity. So typically people would restrict attention to a convex subset to just drop this part. I'm going to write that down, but before that, let me just mention that really I didn't need C1 assumption for mean value theorem 2. I could have just taken an f that is differentiable whose derivative is bounded. Okay. Now, let's write this. Corollary. I have a C1 function. If M is an open or closed ball, in E, so there's a center, and M is really of the form, it's just the open ball center that center with some radius. I don't really care about the center, the radius. Let me say more generally, convex. This just means that given any 2 points, the line segment connecting them is it has to be completely inside the set. Then for any x and y in M, I have the same thing. And in fact, writing that this expression, the sup of f prime over this line segment, you can just switch it to the sup of f prime, rather, norm of f prime. Prime in C0 norm dm xy, and this is upper bounded by the C1 norm, like you did in a previous problem set. You did it for a single variable, but the same idea holds in multivariable also, like this. Okay. So this is just like a slightly lazier way of writing the same thing, essentially. But this does show up in the literature quite often. So you see, if you have a function that is C1 between two open sets, then you get the bound, the distance between two outputs, in terms of the distance between the inputs up to the C1 norm of the function that you're using. Okay. So in a sense, you see, this is, again, something like an operator norm. It's like a nonlinear operator norm, if you want. Questions? I feel like I lost many of you.
Question.
Yes.
So isn't M supposed to be an open subset?
Yes.
Maybe this is a dumb question. Is a closed ball open?
No.
So then why can it be a closed ball? Because it says M is an open subset.
Fair enough. Subset in a. Okay. Good job. Yes. Nice. Okay. Only an open ball. Yes. Thank you. Yeah. That is not a major issue, but because we're just technically you're correct, so I'm not going to involve the lawyers here. So. Okay. Any other questions? Okay, so three consequences of this in value theorem. In immediate consequences, let's say. Well, some of them you're going to deal with in the problem set due this Friday. For instance, based on this, we would like to be able to say things like, oh, if f prime is 0, then the function should be constant, which is what you would expect from single variable calculus. Essentially, it works in multivariable as well, but you have to be careful with the assumptions a little bit. Let me put it this way. Okay, so three consequences. Of mean-value theorem. Immediate consequences. Well, one of them is this theorem that I had mentioned and used when we were doing examples before the break. Namely that a function is C1, let's say a function between spaces of tuples, is C1 if and only if all of its partials exist and are C0. Let me just abbreviate it. All partials are C0. We're going to prove this. Another thing is that if you have a twice differentiable function, then the mixed partials commute, like I wrote early today. Let's say if f is C2, then mixed partials commute. Third, Taylor. Approximation. Well, which says that if f is, let's say, ck, k times continuously differentiable, then f of x plus h is, well, it's, let's write it like this. F of x plus f prime of x applied to h plus f double prime of x divided by 2 applied to h squared, dot, 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 all the way up to, let's say, k. Kth partial of x of f at x divided by k factorial times h to the k plus higher order terms. Okay. Now, there are different formulations of Taylor approximation. But for now, let me just say this. In single variable, it's essentially clear what this should mean, h squared and so on. But what is h squared if h is a vector? How do you multiply a vector by itself? Well, you don't actually. So this f double prime of x applied to h squared is going to stand for something. And so we're going to have to develop some more formalism to handle this. For now, let me just say that once you learn how to interpret this formally or properly in the multivariable setting, this again works the way you expect it to work, as in single variable. OK. Let's do, let me see. Do that later. OK. Any questions about any of this? What do I want to do? I have plenty of time. Let's see. So I'm debating as to whether or not to prove this or to develop the formalism behind this h squared. Well, we did a complicated proof yesterday, so maybe let's take a break today and just define certain things. This proof, the proof of this statement is not very complicated, but it's somewhat complicated. It's not just like a chain rule thing. So let me just switch over to the underlying formalism here. So what is at stake? Okay. Even before the Taylor approximation, we said that, recall, so f is C1. Right. Well, if the derivative exists, f prime exists as a function of x, and it's a continuous function. Okay, so this is in C0. You feed to it a point in the input space, and it gives you a bounded linear operator. Then I define, for instance, C2 to be, well, if f prime exists, and it itself is C1. I said, oh, bounded linears from E to F is a certain open subset of some norm space of itself, essentially. And so f prime is some function between two open subsets of a norm space. So I can recursively define high order differentiability this way. Right, so f in C2, if f prime considered as a function in and of itself is C1. When you differentiate, you reduce the regularity by 1. But what does that mean? So maybe I should be slightly clear. That's 1. That's also 1. What does it mean for f prime to be a C1 function from here to there? Well, using this definition, it means that it has itself a derivative, which should take as inputs points in M, and gives you back bounded linears from the norm space of this to the norm space of this. i.e., okay. Now I told you that when you're doing multivariable calculus, you're going to have to deal with partials. Either you're going to have to do some index management, so the ugliness is there, or you're going to have to deal with these more complicated spaces. And so in the textbook, because we're not discussing PDEs or ODEs and so on, I thought it would be better to discuss this formalism. This is like closer to what the textbook kind of mentions. So for instance, all of a sudden in the middle of like a proof or something, our author starts using the word tensor. So this is similar to tensors. Not exactly tensors, but this formalism is toward tensors. And so the idea is that when you have this bounded linear type of thing, like an iterative bounded linear space, well, you get to rewrite this like so. And then put a subscript 2, say from E to F. So somehow, when you have the space of bounded linears from E to the space of bounded linears from E to F, instead of writing it like this, you write it like this. And if you had, for instance, C3, this would be iterated 3 times. So you would have BLE, 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 F, and you would write it like so. Okay? So you record how many times you're taking input vectors here. And this is not exactly an equality, it's what is called an isomorphism. Okay. And so now I need to describe to you what this means. And this is really the starting point of what is called not linear algebra, but multilinear algebra. Multilinear algebra. Now with linear algebra, we have inputs and outputs, and we have this linear relationship. the main idea of multilinear algebra is that, again, you're going to have transformations that's going to take a bunch of inputs, but with respect to each of these inputs, it's going to be linear, but not in general. Here's what I mean. Let V1 to Vk be vector spaces. And let me take another one, W. I'm going to call a function t from the product of these into W multilinear if, well, if I were to fix all but one entry, that becomes a linear function. Multilinear function is a function t that takes as inputs a tuple of vectors and gives you back another vector in such a way that is linear in each argument separately. We have seen many examples of this so far. Just because it's a different name doesn't mean that you're not familiar with these things. So maybe I should ask you, what are examples of multilinear functions that you can think of?
I mean, for some k, rk is just, the product of k real number spaces, so just adding up all of those.
That's actually linear.
Well, shouldn't it be linear in each argument separately? Like, if
No.
you increase, it isn't? All right.
That's a good point, though. Your colleague is suggesting this into R. Well, let's do R2. X comma y sent to x plus y. This is linear, right? It's a dot product. X plus y is the same thing as xy multiplied by 1, 1. It's a linear transformation.
Cross product?
Yes, cross product is an example. Maybe much more simpler is multiplication. If I were to multiply x and y, that would not be a linear transformation. You cannot write x times y as a linear function of x and y. But if you were to fix x, x times y is a linear function in y. And if you were to fix y, it would be a linear function in x. That's the point of bilinear, okay, or multilinear. So let me write that. You're right, of course. It's just that I don't remember cross products right now. So the formula. Take x comma y, send it to x times y. Well, any inner product is a multilinear function, right? This I can think of as a function that takes two vectors and gives me back a number. And what did it say? Well, if I were to fix the first entry, this thing is linear in the second entry, and vice versa. This is a bilinear function. Okay. Another thing that is very important, determinant. Okay. How do I think about it? For instance, I can think of it as a function defined on the space of n tuples of n by 1 matrices. So determinant is multilinear in columns or rows, whatever. So just to be a little bit more clear about this, what I mean is this. And so well, one of the rules of determinant that I hope you remember from 20 to 70 is that this holds. A1 plus E1. Let's say this is one column, and then A2, A3, dot, 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 AN. These are all columns. So this is an n by n matrix. Well, this determinant is the same thing as the determinant of the matrix without this plus the determinant of the matrix without this. Right? Get to do this. So there are many other multilinear functions. Are we happy with this so far? So this is the linear algebra part, or multilinear algebra part. Mostly algebraic. But of course, in calculus, we need to be able to do, approximations and so on. And so now I would like to take, instead of arbitrary vector spaces, I would like to take normed spaces and start talking about continuity. At this stage, I cannot really talk about continuity of something like this. But what I can do is this. And in fact, let me also introduce some notation. So the space of all multilinear linear functions like this, I'm going to denote by L sub k, and then from here to there. All k linear or multilinear. And typically people don't keep writing V if each of these factors is just the same vector space. Okay. And so, just like we did for linear transformations, we would like to be able to talk about bounded multilinear operators. If all of the vector spaces involved are normed, then for T k-linear, define the operator norm. Well, how to do it? Well, you can feed to it k arbitrary vectors, and then look at the norm of it, of the output here, and try to bound that norm using the norms of the inputs. Right? That's how you define operator norms. It's basically the same definition that we're used to from week 2, I think. So T, V1, V2, dot, 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 Vk, I feed to this multilinear guy, k vectors, look at the norm of the output, and I want this to be bounded by, well, c times the product of the norms. And here, v1 comes from v1, v2 comes from v2, and so on. For vi and vi. Does this remind you of something? You have, in fact, seen this. I didn't write it as the operator norm, but you have seen something like this in a previous problem set. No? Well, much like number multiplication is bilinear, so is matrix multiplication, or more generally, operator composition. In a previous problem set, we had this. If you have two operators that you can compose, and you take the operator norm of this, this is bounded by the norm of this guy times the norm of this guy. Yes? And so really, you can think of this as a statement about K and L, or you can think of it as a statement about composition or matrix multiplication. So really, in that problem set, what you were showing was that the operator norm of matrix multiplication or operator composition itself is at most 1, or is equal to 1. And you see, this is not a super far-fetched thing to think about. Let's say just matrices. This is bounded by A in norm times B in norm. So this statement is really about matrix multiplication. And so matrix multiplication is important to be able to do. It's important to be able to do efficiently. And so maybe you can try coming up with operations that take two matrices and produce something actually that is the matrix product, or something approximating the matrix product, with some small error. So you see, it's important to be able to think about matrix multiplication itself as an object within linear algebra. OK. And so if you're interested in these kind of things, there is something called alphatensor, I think. That would be worthwhile checking out. How do you even matrix multiply more efficiently? OK. And so just like with linear transformations, if the operator norm of a k-linear map is bounded, I'm going to call it bounded k-linear. T is bounded, multilinear or k-linear. If operator norm is bounded the set of all bounded k-linear operators I'm going to denote by B L sub k. And just like we did with linear transformations, operator norm for k-linears is a norm on this space. Okay? And if W is complete, so is this. And in fact, a k-linear transformation is bounded if and only if it is continuous. So everything that you're familiar with within the context of linear algebra or norm spaces apply pretty much verbatim to k-linear transformations. Okay? I'm not going to prove these. Big exercise. Anything you can do for bounded linears, essentially you can prove for bounded k-linears. And let me just mention this as a theorem. We're not going to have time to discuss it any further. Now I can say this. No. So k, maybe just say 2. Bounded bilinear transformations from V to W, this itself is a norm space, is isomorphic as a norm space to the space of bounded linears from V to bounded linears of V taking values in W. So what you get to do is either you can think of a bilinear transformation that takes 2 inputs, or you can just say, I'm first going to feed to it one vector, and then I'm going to have a transformation that takes another vector. We're going to discuss that tomorrow. Thank you. I'll see you tomorrow. OK, let's start. Good morning. So today I'm going to be taking attendance. Please make sure you sign your name. So today I'm going to mention a couple more words about this multilinear algebra stuff. We don't really need a deep understanding of this. I'm just discussing this so that we can understand Taylor approximation in this more general multivariable setting. A small change of plans. Probably what's going to happen is that yesterday I mentioned 3 immediate consequences of the mean value theorem. One of them was, a function is differentiable if and only if, or let's say C1, if and only if all of its first partials exist and they are continuous. That was the first consequence of the mean value theorem. Second consequence, I said, if you have a twice differentiable function, then the order of the mixed partials doesn't matter. And then the third consequence was, there's Taylor approximation. Now, after the class yesterday, I felt like I was losing a lot of you. So what we're going to do is we're going to prove only the first of these 3 consequences. The other 2 I'm going to state, and you have every tool that you need to prove them. But instead of proving them, actually what I'm going to do is I'm going to take a specific function and do certain things with that example. Okay? And so that's going to take the rest of this week. Next week, we're going to be done with Taylor approximation by the end of this week, hopefully. Next week, instead of starting integral calculus, we're going to work on the inverse function theorem and implicit function theorem. So this is the second important item in this class. Just like you have, let's write it like this. y equals c, dx plus dy equals f. Given a, b, c, d, e, and f, you now know how to solve this for x and y. This is the point of linear algebra. Of course, you didn't need matrix algebra to solve this, right? You could solve this equation for y and then plug it into the other one. And in principle, too, you don't need linear algebra for systems of n equations with n unknowns. It's just that matrix algebra makes things a little bit more systematic. Well, inverse function theorem basically does the same thing when you have things like this. Let's say this is sine. Sine of x, d times sine of x. Now, solving this equation for x and y is more complicated. This is not a linear equation now. But at the very least, each of the components are differentiable. So even though you cannot do linear algebra, you can do the next best thing, which is calculus. Calculus is basically things that are approximately linear. And so inverse function theorem, when it applies, allows you to solve equations like this. OK, I should be more clear. Allows you to show that there's a solution to this. It doesn't necessarily tell you what the solution is, right? This is similar to how, in the linear case, for instance, we have really two concerns. You can ask, oh, does this have a solution? To answer that question, you don't need to actually solve for it, right? You could just look at the determinant, whatever. There's a unique solution, whatever. Inverse function theorem, too, just essentially, in principle, just tells you that there's a solution. It doesn't actually tell you what the solution is. But we'll discuss, well, let me put it this way. Inverse function theorem has many proofs, and the proof I'm going to present actually gives you an algorithm that converges exponentially fast to the inverse, to the solution. So we'll see. Needless to say, inverse function theorem and its cousin, implicit function theorem, these are very important ideas from calculus. So I don't want to rush them, and we're going to spend plenty of time. Now, I had listed some optimization stuff. So critical points, then the first derivative test, second derivative test, right? So it's like if you're trying to understand a function, you differentiate it, set it equal to 0, the derivative, and that tells you sort of like local maxima or minima. That is, again, true in multivariable, but you would need to develop some stuff. And there's a second derivative test. So in single variable, you have this, you look at the second derivative. If it's positive, it's convex, or it's a minimum, blah, 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 right? There's a similar version for this. For multivariable, you look at the second derivative again, and that tells you things in pretty much full analogy with the single variable case. So I'm going to probably skip all that stuff. Part of the reason is that you'll likely see discussions of these ideas in many other classes as well. On the other hand, things like, the inverse function theorem often doesn't get discussed that much. So I'd rather focus on these. OK, are there any questions? OK, so back to this multilinear algebra business. So what was the point? The point is that instead of having a function that depends linearly on one input, right, so you had something like this. This was linear. And so we were now looking at, let's say, v1 plus w1, and here, let's say, v2. Say now t takes two inputs. These inputs are allowed to come from arbitrary spaces. And so now, instead of asking for this, I want the following property. If I have two inputs, if I fix the second input, that is to say, the input coming from the second channel, using sort of control theory if you want, I get to split the outputs in the first channel. Okay. And likewise, if I were to fix one input in the first channel, then I get I have the linear relationship in the second channel. That was multilinear. Now, technically, linear is the same thing as one linear. And so yesterday your colleague said, oh, your colleague gave the example of an addition as a multilinear map, and I sort of objected to that. I said that's linear. But then when you think about it, technically linear is multilinear. But no one would use it that way. Okay, so linear is one linear, if you want. But whenever you see multilinear, you should think at least 2 entries. So this is bilinear, for instance. This is one of the sort of unfortunate consequences of nomenclature in math. So for instance, when you think about it, continuous functions are also not discontinuous, right? Or there's a bunch of other things. Or linear functions are actually also nonlinear, because when people say nonlinear, they don't mean the complement of linear. They mean possibly nonlinear. So pet peeve of mine. It's it's tradition. Okay. Any questions or comments about any of this? So here's a theorem that I mentioned. If I have 3 norm spaces, V, W, and X, well, I have first the space of bounded bilinear transformations from V times W into X. So in the first entry, I'm allowing V vectors. In the second entry, I'm allowing W vectors. And if I were to fix this, then the function is linear. Or if I were to fix this, then the function is linear in the remaining variable. This is the left-hand side. And there's an operator norm. Right? So you just look at the relationship between the magnitudes of the inputs versus the magnitude of the output. And you sort of relate them, and that gives you a number. Much like in the case of the operator norm for linear transformations. And on the right-hand side, we have first the space of bounded linear transformations from W to X. This in and of itself is a norm space. So I get to plug it in, consider it as a norm space in and of itself, and then consider the space of bounded linear transformations from V to the space of bounded linears. And again, as ultimately this is a space of bounded linear transformations, there's an operator norm on this. And relative to this operator norm, this whole thing in and of itself is a norm space. So left-hand side is a norm space. Right-hand side is a norm space. I'm saying that these 2 spaces are isomorphic as norm spaces. And in fact, they're isometric. I'm going to mention what this means. And here's another word that I'm not going to discuss too much. I just wrote it there because some of you are taking a class in category theory right now. So it turns out that this word natural is a technical term. Okay? And somehow this equivalence, this isomorphism, is essentially the only way that you can do this. You can establish an isomorphism. There isn't that much choice involved. So I'm going to leave it to you because fundamentally it's not a sophisticated idea and it's not central to our concerns. Proof. All I'm going to do is I'm going to give you the usual suspect. Let me put it this way. So how do you show that this is isomorphic to this? Well, you need to show me, you need to tell a linear transformation that is bounded, that has an inverse. Its inverse has to be bounded also. Using this. And here's the idea, okay? It's a very natural idea indeed. You say, okay, if I start with a function that takes B and W as inputs and gives you back X, some other thing, as the output, well, what I can do is I can first fix the first entry and then think of it as a function of the second entry. And so this is what you do. let's say so you have something like this. You can, if you have a function like this, you can think of this as a function, as a bivariate function that depends both on x and y, and differentiate it that way. Or if you want, maybe you're just interested in the partial derivatives, for instance, you can say, OK, I'm going to fix x, and then think of it as a function of y. It's almost like doing nothing, OK? I understand. This is why this is kind of confusing. But this is the idea. So the point is, this idea of fixing one of the variables itself gives you this isomorphism, OK? And in computer science, this is what is called currying. Some of you are aware of this idea. Curry was a logician, I guess, and computer scientist. Currying. So phi, from the left-hand side to the right-hand side. OK. Just going to write it like this. So you feed to it a bilinear function. He takes two vectors, gives you back one vector. Now out of this, I want one function that takes vectors, gives me back functions. So at a vector v, it will be a function from w to x. And how do you do this? Well, to this function, you feed w, and it gives you back this thing. This is the formal way of describing this idea of fix one of the variables and consider the remaining function. The perhaps miraculous thing is that this phi itself turns out to be a linear transformation. It turns out to have a linear inverse. It's bounded. It's a bounded operator. Its inverse is a bounded operator. And furthermore, this isometric property means that if you have a bilinear function here, you can look at its norm here, or you can look at the norm of its image under currying. It turns out that these two norms are the same. So for free, you get to think either as a bilinear function or a function of functions. The operator norm of the output is the same thing as the operator norm of the input. This is the isometric property. So that means that ultimately, what we need to know for the rest of this class, for the rest of this course, you get to reshape your multilinear functions as iterated linear functions for free. OK? You get to reshape for free. That's all we need to remember. So here are some more exercises. Once you have this, you can just, by induction, take many vector spaces like so. Okay. And so let me write it perhaps here. Likewise, this, okay, bounded k-linear that goes from B into bounded L-linears is the same thing as the other way around, or if you want, you can collect everything and write them as k plus L linears. Well, let me just write it like so. Isometrically. Okay. This is confusing, I realize. I'm not going to use it any further. All you need to remember is that you get to reshape this multilinear stuff for free. So the point you get to reshape multilinears for free. Free real estate. Okay, that's all you need to know. Now, there's something even deeper going on within this context of category theory, where this phrase is really contextualized. In category theory, people look into expressions like this and think of the spaces themselves as variables, and for instance, this BL itself as a function. So this is like a meta level of doing math somehow. Sometimes it is useful, not for us that much. In analysis and calculus, it's not often very useful. But if you're interested in sort of these meta ideas, it's sometimes fun. So they call BL, not a function, but they call it a functor. Okay, it's like, there's a bunch of things. These type of things kind of hurt my brain, so we're not going to continue. I'm just mentioning these because some of you are taking category theory right now. And probably you're sort of seeing some patterns, and you're not mistaken. That's all I want you to get from this. OK. What else do I want to do? Oh, one thing I want to define. Now that we have things like this, we can define polynomial functions between open sets of normed spaces. Really, this is what I'm interested in. Because when you think about Taylor approximation, I have a function, and I get to approximate it using a polynomial. Now, in single variable, it is clear what a polynomial is. And maybe in multivariable too, if you have spaces of tuples. But ultimately, I would want a notion of a polynomial that would work for normed spaces. And this is how we define it. You define it using multilinears. A polynomial function from M to N, these are my usual open subsets. Is a function of the form let's write it like this. Let me write it like this. Is a function such that there is T0 in N, T1 bounded linear from E to F, T2 bounded bilinear from E to F, and so on, all the way up to, let's say, a bounded K linear. Such that for any x in M, the value of P at x is nothing but, well, you just take this x and feed it to all of these. T0 plus T1x plus T2. But you see, T2 now takes two vectors. And so what am I going to do? I'm just going to feed the same x into it. T3 takes three inputs. I'm going to feed the same x into it. Okay? Tn x x dot 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 x. K. K many. This is how you define a polynomial in general. Now, is a polynomial function that you're familiar with in the case of single variable of this form? Well, certainly, because let me just give that as an example. So a polynomial function is a polynomial function. And so if I have something like this, right, so a0 plus a1x plus a2x squared plus dot 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 plus a k x to the k, well, how am I supposed to think of x squared and so on in terms of multilinears? Well, I'm going to say x squared is really, so t0 here is a0, t1 is just x, t2 is supposed to take two inputs, two real numbers. Well, it's just going to be just multiplication of them. T3 is going to be xyz, t4 is going to be xyzt, and so on. So t3, so maybe I should write x1, x2, x1 times x2. This is x1, 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 x2, x3 goes to their product, and so on. Okay. You just take k many numbers, multiply all of them, and these give you the components of polynomial functions that you're familiar with. Okay. So in this case, let's say t goes from r to r. So t1 is going to be from r to r, t2 is going to be from r times r to r, and so on. Right? So tk is going to be from r to the k to r. Okay. That's okay, maybe I should say one more thing, one final thing. When we think about Taylor approximation, then this h squared, h cubed, and so on, well, they better stand for the idea that you just feed the same vector into the corresponding multilinear parts. To the second derivative, you plug in h 2 times like this. Okay. For the third derivative, you apply the third derivative to h, and so on. So when we see in the Taylor approximation h cubed, h to the fifth, and so on, that's all you're doing, really, in the multivariable setting. Okay? So that's all I wanted to say about this multilinear stuff. More important is this theorem about the first partials. Any comments about any of this? So like I said, this is one of the three immediate consequences of the mean value theorem, the theorem that I'm going to discuss now. I'm going to take my time proving it. I'm not going to prove the other two. And instead, we're just going to look at an example. So theorem. How to state this? Well, let me state it like this. So we have M is an open subset in E, and N is an open subset in F. I want something like this. If a function is, well, if all partials exist, then the function should be differentiable. And so what I'm going to say is, I'm going to split. So suppose the input norm space into two pieces. I'm assuming that E comes from E1 times E2. That is to say, any vector in my norm space E is a pair of vectors, V1 and V2, where V1 comes from E1, V2 comes from E2. Okay? Then f is C1, it's a C1 function from M to N, and its derivative is made up of these derivatives of the partials. Let's say df equals d1f, so the first partial. I'm going to write down what this should mean. So here I'm using sort of a matrix of operators. I'll tell you what this means also. If and only if for any x, which is a pair of numbers, a pair of vectors, in M, the first partial and the second partial exists, and they are both continuous. Exist and are functions of continuous functions of x. What does this mean? There's a bunch of like notation. Now, I had given as a previous exercise to define these partial derivatives in the case when your space is split into components like this, arbitrary components. But let's open these up, try to understand what we have and what we're trying to prove. In fact, even before that, even before understanding this syntactically, let's pretend that E is R2. Okay. So I'm writing this as R times R. And I'm saying that f is C1 from an open subset in the plane to some other space. And the total derivative is now the x partial and the y partial. Okay. So this would be the x partial, and this would be the y partial. If this abstract formalism is confusing you, all you need to know is that it is defined, everything is defined, so that you get to pretend that this E1 is pretty much R and so on. And this D1, the first partial, is pretty much the same thing as this. In particular, I get to draw this, okay? Anyway, let me say this as well. And so when I write it like this means that df xy, which is the same thing as the derivative of f at xy. And so when I say this is the same thing as this, what I'm really saying is this. Okay, I'll leave it as this. This is this applied to a vector, h1, h2, is d1f plus d2f. This is what I'm trying to show. Okay. So I have the right-hand side. This is well-defined. This is well-defined. This is an if and only if. So the forward direction is OK. The backward direction is the complicated part. Looking at this part. So we're given this, and we're given that this depends continuously on the base points. And this too is, it depends continuously on the base point. We want to show that if this depends continuously here, and there's a continuous dependence here, then you get to assemble both of these and write them, combine them into the complete total derivative. That is what is at stake in the backwards direction. This is what is happening. So now let me try to draw a picture to interpret this whole thing. In fact, I'm going to do it here. I'm just going to pretend that E1 is the horizontal axis, E2 is the vertical axis. M is a certain blob in this E space. Okay. I have F, goes to this other space F. And in it, there's a subset N. Okay. Now, I take a point. Okay. Its components are, let's say, x1 and x2. So if the name of this guy is x, here I see x1, here I see x2. And when I apply f to it, it goes to some point, okay? It goes to, let's say, to this point, f of x. Okay, so far? Now, what was the derivative about? The derivative was about this. I wanted to, so I had some input-output relationship, and then I perturbed the input just a little bit. And I wanted an explicit relationship, a linear relationship between the change in the output as a function of the perturbation. Okay, that was this first order approximation business. Okay, so here's what you do. Now we need colors. Maybe this as well. Okay. Because f in principle is a function from this m into n, you start with x plus h, something like this. Okay, this is a small perturbation. So this is a point, and h, of course, is this vector, right? This small perturbation h has its E1 components and E2 components. So this would be x1 plus h1. h1 would be a vector in E1. Okay, so maybe I should draw these with red. Arrows, velocities are in red. Okay. And likewise, in the E2 components, here there should be x2 plus h2, let's say, and there would be a vector in E2 that would take x2 to h2. Okay, so far? Now, when we're going in the backwards direction, that is to say, if we have the first partial and the second partial, we have the following ability. I don't get to immediately look at this, the effect of perturbation in this direction, but what I can say is that, oh, perturbation in the h direction is nothing but the perturbation in the h1 direction, so it's a horizontal perturbation plus a vertical perturbation. Okay? And so the point is that instead of directly looking at the effect of this, first I'm going to look at the effect of the horizontal perturbation coming from the horizontal components. Then to it, I'm going to add the effect of the vertical perturbation. So instead of directly going from here to there, and let me also say this small point, so this nearby point also is here. Okay. And so first, instead of going from here to there, I want to just restrict my attention to the horizontal motion. That is to say, what I'm going to do is this. I'm going to look at this horizontal piece. Under F, it turns into something. Now, when I apply F to it, because F is a nonlinear thing, I don't know if it's a line anymore, even. Okay? So the image of this horizontal piece under F is going to be something crazy. Okay? So here is x1 plus h1 comma h2 comma x2. This is a small horizontal perturbation. All I know is that the image of this blue point is going to be on this path by definition. Okay, so this is f of x1 plus h1 comma x2. But now, instead of actually going through this nonlinear thing, because I know that the horizontal derivatives exists, I'm just going to approximate the effect of this horizontal perturbation using this linear term. So I'm going to say, oh, instead of doing this, I have an approximation. I have a good enough approximation. It's like this. Okay, so this is the approximate. So what is the approximation? It will be f of x plus d1f times h1, up to higher order terms. Okay. This is my first order approximation using only the first partial. There is some error there, but that's okay. Okay, so far? And so now, what am I going to do? Well, I'm going to go from here to there now. Let me just take a different color. Now, once you have the picture in mind, what needs to be done becomes more clear, I think. And so now, instead of looking at the image of a horizontal piece, I'm going to look at the image of a vertical piece. So it's this one. Okay. Oh. So, okay, so that's that. And again, under this nonlinear transformation, f, this vertical segment is going to be something very crazy, because it is nonlinear after all. But all I know is that the image of it has to pass through the blue point, rather the image of the blue point. The only thing I know is that this is what happens, and indeed it has to pass through the image of x plus h as well. So this orange segment, which I'm drawing as a line, but it doesn't need to be a line, has to pass through this and this. Okay? But you see, and like we did with the horizontal first order approximation, from going here to there, I have another approximation, maybe like so, somewhere here, or maybe let me draw it like this. Okay, it's more clear. So this now is, well, it's this point. That's where I started. And then I'm going to correct it using the second partial, because I'm moving only in the vertical direction. Plus h2, okay? But here's the problem. I had already started with a perturbation, with an approximation. So really, if I'm trying to approximate this point, which was what I wanted for the differentiability of f, well, somehow I need to add this to this. So what I'm going to do is I'm going to take this second part and move it so that the two arrows are joined. Okay, so this is the cost. Instead of going from here to there and approximating in the first order, which is what differentiability of f allows you to do, you say, oh, let's say if I have just partial derivatives. Then in your approximation, you're going to have to approximate in the horizontal direction first. That's going to give you some error. And then in the vertical direction, that's going to give you some other error. What might happen is that the errors might add up. And then even though in principle this looks like it works, maybe this error is not sufficiently small. Okay? Maybe the errors add up too much, and you cannot control it. Does this make sense? That is what is at stake. In terms of, well, matrices, if you have space of tuples in the output and output, in the input and output spaces, this is just this idea that, oh, a function is differentiable with continuous derivative if and only if all of its partials exist and they are continuous. In other words, you get to build this matrix of partials if and only if each partial exists and is continuous. We have seen how it might happen that each partial exists, but they don't compile into one big matrix for the derivative. There, what was happening is that you were sort of approximating in the first direction and then the second direction and so on, and these errors added up, and you couldn't control the error. That was what was happening underneath. Okay. Any questions about this? This is an important idea, and I would highly recommend that you slowly sort of draw this picture. And again, let me remind you, how do I get to just pretend that everything is like two-dimensional and this is a line and that is a line? It's ultimately because of the formalism that we developed. Okay. And now, I'm going to leave it to you as an exercise because I don't want to start the proof of this today, that by essentially induction, you can sort of generalize it in many different directions, this statement. So consequences, exercise. In fact, you can do another induction and the number of differentiability to get C2, C3, C infinity if you want. State and prove results regarding many variables, many components, let's say, and many derivatives. Okay. Maybe k components or n components and k derivatives, infinitely many derivatives too. You can do that too. Ck, C infinity. Now, what this doesn't allow you to do is to go one step further beyond infinitely many differentiable and put the derivatives into a series and make it converge. That's a different thing. That's the next level. We're not going to discuss that. You have seen some stuff with the exponential function and so on. That was, exponential functions are they're better than C infinity. Okay? They are analytic. They're really real analytic. They have power series that converge. This argument is not going to cover that real analytic stuff. That's the limit of what you can do with this. But all the way up to infinity, you can go. Okay? So we're going to discuss the proof of this on Friday, and then we'll be on our way. Thank you. Okay, so in today's class, I had a technical issue, and my microphone didn't record the audio, so I only have, video footage. So I thought what I would do is I would just watch the silent footage and commentate, and then I think this footage I'm going to superimpose and sort of edit in. Okay. Okay, this is the beginning. So today's class is all about the proof of this theorem that a function is C1, continuously differentiable, if and only if its partials exist and are continuous. And so I didn't do anything different than that, because I took my time today writing down the hypotheses and what we're trying to show slowly. Okay. And I have written down an exercise, and at some point I think I said something along the lines of, oh, we're going to prove this, but in fact, the argument that we're going to be writing down works for the exercise as well, which says that if the first and second partials exist, and at least one of them is continuous, then in fact you can assemble them into the so-called total derivative or differential. And I guess now I'm talking about the change in the schedule and in the syllabus I made. So basically, we were behind schedule, and I think I had reserved 3 weeks for differential calculus. And then right after that, we would next week start with integral calculus. So instead of having integral calculus next week, we're going to have differential calculus 4, I think. But we're not going to be pushing the midterm, which is in 2 weeks. Okay. No, I think right now I'm describing this exercise that I wrote down. I should keep in mind that you're going to be able to see what I'm seeing right now, even though in the footage that I'm recording now, I'm not recording what I'm seeing. Okay. Okay, we start the proof. So one direction, I think I left as an exercise. So if the derivative exists, then you index in the certain components, and so that the forward direction is not that complicated, let's say. So I left it as an exercise. The problem is, if you have d1f and d2f, and if they are continuous, how are you going to assemble them to get the complete or total differential or total derivative? Yeah, I decided to use the boards in the back for the first time. It's kind of awkward to use the boards in the back because they're supposed to be able to go higher up, because otherwise the front boards obstruct the vision. And so I'm writing down the hypotheses. First hypothesis is that d1f exists. And so by definition, it should be a function that goes from M, the open sets on which f is defined, and d1f should take values in the space of bounded linear transformations from E1, so this is the horizontal component of the input vector space E, into f. So now we need to write down, I think I'm going to write what it means for d1f to exist, really. I guess here I made the point that d1f, when you think about it, it should be something about first order approximation, but only for horizontal perturbations. I had in fact given as an exercise before defining d1f and d2f. These are essentially generalizations of partial derivatives. Okay. So now we're going to write down the definition of d1f, or rather d1f existing. And so for any x in M, and because M, so the vector space associated to M is E, and it has two components, E1 and E2, I can think of the point x as having two components also, x1 and x2. And so what am I going to do? I'm going to take the space point x, x1 and x2, and I'm going to perturb it only in the horizontal direction. That is to say, I'm going to add a small infinitesimal, so to speak, vector h1 only in the first component. And I'm writing down the standard ratio that one would use to define derivatives. Now d1f at x1, x2 is supposed to be a linear transformation from E1 to f. And so if my small perturbation vector is h1, I get to apply d1f to it to get a vector in f. So in the numerator, I have a bunch of things, and they're all vectors in f, so I can just take a linear combination of them and look at the norm of this. In the denominator, because the perturbation is horizontal only, I should just look at h1 in norm. But because the horizontal perturbations correspond to the E1 component, I'm going to look at the E1 norm. And so that's why I wrote it like this. I think that's where I made a horizontal movement. Yes. I'm going to be livid if this time the audio doesn't work also. I feel like it does this time. Okay, so now I'm sort of looking at the types of all of these symbols, trying to make sure that everything makes sense. In a numerator, okay, and then I say, okay, I'm going to take the norm in f, in the output vector space. Okay. When I'm watching myself, time flow so much slower. It's like when you're describing these kind of things, it's like it feels so much faster. Interesting. Oh, I say d1f existing means that there is a bounded, so that for each point x1, x2, there's a bounded linear d1f x1, x2 from E1 to f, such that, well, that limit is 0. That is the definition of what it means for d1f to exist. Okay, and then I say, I think, here that pretty much the same way you define d2f. And so instead of now looking at horizontal perturbations, you want to look at vertical perturbations. That means you take x1, x2, and instead of adding h1 to x1, you add h2 to x2. Okay. And instead of h1, I'm going to have h2 and so on. Okay. And again, once you look at everything, it's like it still makes sense. So it's pretty much analogous how you do this. And oh, I also have the hindsight, of course. I kind of remember what happened. And I think here, yeah, I gave it as an exercise to write this definition of what it means for d2f to exist explicitly, even though it's pretty much the same idea. A big, I think, complication in multivariable calculus is that we have all these like notations and terminology and stuff that allows you to compress a lot of these ideas, but then it becomes sort of abstract. It starts feeling abstract and like you start losing what you're actually doing. So it's a very good exercise to write things down explicitly, at least like a couple times. And now I think, yeah, I'm switching over to d1f being in fact a continuous function. So on the left board, we described the hypothesis of it existing. And now I want to say on top of that, it is a continuous function. And how do I make sense of this? Well, I say M is an open subset in a norm space, which is E. And I say BL of E1, F2 is an open subset in some norm space, because any norm space is open in itself, and spaces of bounded linears, certain is a norm space. And so once I have two subsets of two metric spaces, and norm spaces are metric spaces, and once I have a function between two subsets, well, I can ask whether or not this function is continuous. And that's what I'm doing here. And I think in a second I'm going to write down this continuity hypothesis for d1f. For any x, x1, x2, I think here what I said is that, oh, what does it mean for a function to be continuous? It means that the function is continuous at any point. So it's a pointwise property after all. And then once I fix an arbitrary point, x, I can write down explicitly what it means for d1f to be continuous there. And that is what I'm doing. And so you see I have a small h1, small h2, and I'm comparing the values of d1f at x1 plus h1, x2 plus h2, and the limit point, which is d1f at x1, x2. And I'm going to take h1, h2 to 0, and I want this limit to be 0. And I think at this point I asked something about, oh, what is this norm? So where is this norm being taken? It's sort of like a sanity check, if you want. So this is, I think, at least from when you're first trying to learn these things, it's good to keep in mind or keep track of where certain functions take values in and what the norms are with respect to. But of course, once you get comfortable with these ideas, it's like you can just stop writing things explicitly more. Yeah, here's where I'm asking, where is this norm in? And well, one of your colleagues did say, oh, it should be an operator norm, right? Because once you feed to d1f one input point, x1, x2, now the output is a bounded linear from E1 to F. So it should be an operator norm. Or I said, if you want to be a little bit more specific, you can just write down the name of the normed space, which is the space of bounded linears. And that's why in the subscript I'm writing BL E1, F. Okay. So we have one final thing that we're going to write here. So these are all the hypotheses. Oh, there's one for D2F, of course. We're assuming that D2F exists also. So let's write that down. I'm just going to say similarly, and I'm going to leave it as an exercise to write it out explicitly for you. Okay. And I think this was nice in the following sense too. A big part of calculus is, well, actually writing things down. And I personally remember really appreciating it when every once in a while, you know, my professor would sort of write these expressions out explicitly, take the time, and it's like slowly write everything down. And that was sort of, you know, make it clear to me that this is how you do it, right? It's a rather simple but very powerful trick, because a lot of math notation is designed to compress a lot of information. For instance, think about like a summation or whatever. A very nice thing to do is to just open it up, and it makes things in my head, as I'm sort of first learning a certain thing, easier to follow. And so now I'm writing out explicitly what it is I'm trying to prove in the backward direction. So what does it mean when I say df equals d1f, d2f in a matrix? Later I'm going to mention this. Right now I'm already using this, well, matrix of operators notation. In a second I'm going to tell you how we can make sense of that matrix algebra with matrices, with operator values. But for now I'm just going to write it explicitly. So from a practical point of view, I am trying to show that a certain limit is 0. And so I'm going to explicitly write down the limits. And the point is that the existence of df really means that instead of just focusing on horizontal perturbations and vertical perturbations, you're supposed to allow arbitrary perturbations. That is to say, perturbations that have both horizontal components and vertical components. And so that's why I have f of x1 plus h1, so that's a horizontal perturbation, comma x2 plus h2. And now it has a vertical perturbation also. And I'm saying that, well, the linear part, or linear response, should be d1f at x1, x2. So now that's a bounded linear from e1 to f. I can feed to it h1 to get a vector in f, plus d2f x1, x2, which is now a bounded linear from e2 to f, which means that I can feed to it h2. And so now I have ultimately a bunch of vectors in f. I can take their linear combination in the way I do, and then take the norm in f, and divide everything by the norm of the complete perturbation, which is h. H is the vector which has components h1 and h2. And I should be taking the norm in E. And I think now I'm going to say something about this matrix of operators. So really, when I write on the bottom left board, df equals the row matrix, 1 by 2 row matrix, with components d1f, d2f, I would like to think of it really as a 1 by 2 matrix. And I say, well, let's see how I'm going to write it. Well, I'm going to take a small perturbation h, which is an H1 component, horizontal component, and a vertical component H2. And I'm going to write that H as a column matrix with entries H1 and H2. I'm saying, oh, this tuple of vectors, I'm going to think of a column matrix with vector entries. And okay, not enough space. I'm going to delete it. Okay. Every semester there's like one of these classes like this. Something goes wrong. And yeah, I say, okay, I'm going to think of this D1F, D2F as a row matrix, and the inputs, the perturbation vector H, as a column matrix. And this is pretty much like a dot product for me, or, matrix multiplication. Exactly. And I think I said something about, oh, there's actually like a formalism behind it as well. I said that this is comparable to this block matrix stuff. And here I'm writing, oh, okay, we're used to this notation of a curly m of n times m, comma r, and we varied n and m to represent different dimensionalities. But then I say, oh, instead of r2, I can put other things. So instead of r, in this case, I will put some space of operators. And then I said I'm not going to develop this any further. It is useful being able to think about this, but it's not the main concern of our class. We're halfway there. And I think right now what I'm saying is, instead of looking, so I know what I want. It's on the top right board at the bottom. And then I say, instead of looking at the ratio, I'm just going to look at the numerator. And I'm going to try to bound it by epsilon times the norm of the perturbation, which is h1, h2 in norm. Yeah, I think what I'm saying here is that I have here f of x1 plus h1, comma x2 plus h2, and that is both a horizontal perturbation and a vertical perturbation simultaneously. So I'm going to add and subtract some terms so that I'm first focusing on the horizontal perturbation and then the vertical perturbation. And honestly, I'm not super unhappy about this arrangement with using 4 boards. Yes, like the front ones are obscuring the back ones, but maybe I'll be able to use them. I don't know. Yeah, so now I'm saying, I'm just going to think of H2, the vertical perturbation, as fixed, And I'm just going to focus on the horizontal perturbation h1, this one. And in a second, I'm going to realize that probably writing along the full board is going to be more useful. Okay, I'm going to try again, I guess. Okay, we're trying again. There you go. Okay, let's try that again. Okay. So you see, okay, so this is what I'm trying to handle. This is what I want. I want to be able to bound this in norm. Okay, that's the affine transformation over there. And I'm trying to bound that by epsilon times the norm of h1, h2. I say, oh, you see, this is correct. This is what I said I wanted to bound. And I'm going to add and subtract some terms. Oh, okay, I decided to put the norms there as well. And so now that I have norms included in the situation, when I add and subtract terms, and once I start distributing the norms, by the triangular inequality, I may not have equality still, but at the very least I know that the new quantities are going to be not less. So they could grow, but they're not going to decay. So first I'm fixing the vertical perturbation, and I'm focusing on the horizontal perturbation, which means that I should be using the d1f, horizontal derivative. Okay? But I added some new terms now. So I need to, well, I subtracted technically, which means that I need to add them back up. Because ultimately what is happening here is that you have a linear combination inside a norm, and first, forget about the norm. You add and subtract certain terms so that it's equal still. You still have equality. Then you put norms that encapsulates the whole big mess, and then you distribute the norms in an appropriate manner using triangular inequality so that you have this less than or equal to. Yeah, I say, okay, in the second part I have now, I'm focusing on the vertical perturbation. Okay, and then I'm looking at the remaining terms. And what is remaining is, well, d1f at x1 comma x2 plus h applied to h1 minus d1f at x1 x2 at h1. And these are all still vectors in F, which means that the norms are going to be in F. And then I'm going to say something about collecting the H1 terms in the third third summand. Because after all, it consists of two bounded operators, d1f, at different points applied to the same vector. Oh, before that, I'm reminding you of the triangular inequality. I say, oh, if I have a plus b in norm, it is upper bounded by a norm plus b norm. And technically here, I'm applying triangular inequality 2 times. Okay? And I say, I think I'm trying to justify here why I added and subtracted some terms and split them this way. I'm saying, oh, the first one I can control because I assume that d1f exists. So horizontal perturbations up to first order I can manage. I can bound that first summand using epsilon times h1 in norm. And then likewise, because I'm assuming that d2f exists, I can handle vertical perturbations, which means that the second summand I can bound by epsilon times norm of h2. And then the third one, now I'm going to collect, I think. Here I say, OK, these are two different linear transformations from E1 to F applied to the same vector. And so I can collect the matrix or operator parts. After all, I can take two operators from between the same spaces and take their difference. That's still an operator. Apply to H1. And then I can distribute the norm over. And so AV in norm is bounded from above by A norm times V norm. This was like something that we've been using all along. And so I collected these terms. And so now I have the difference between d1f at x1, x2 plus h and d1f at x1, x2. These are operators, so I'm looking at the operator norm from E1 to F times h1 in E1 in norm. So okay, so the first summand I can control because I assumed that d1f exists. Horizontal perturbations are fine. The second summand I can control because I assumed d2f exists, so vertical perturbations are fine. Okay, now I'm looking at the third term, and I say, oh, but also I assume that d1f is a continuous function. And so for h2 small enough, that is bounded by epsilon, that norm, that operator norm, epsilon times h1 in norm. Okay, so now we collect everything. I didn't write down all these things, so when you even further open up these limits, of course, it says for any epsilon, there's a delta 1, such that for any h1 and e1 less than delta 1 in norm, well, that first summand, for instance, is bounded by epsilon times h1 in norm. And similarly for h2 and so on. And so I have that. And then I say I have two copies of h1 in norm and one copy of h2 in norm. Well, I might as well just add one more copy of h2, why not, to get a nicer looking expression. 2 epsilon times h1 in norm plus h2 in norm, and I might as well think of h1 in norm plus h2 in norm to be the norm of the complete perturbation h, which is what I do. And that's the end of the proof, I think. Yeah, okay, so I say, okay. For any epsilon, so I'm saying out loud again, for any epsilon there's delta, all that stuff. Such that for any h1 less than delta, all that stuff. The numerator that I'm trying to control is bounded by 2 epsilon times the norm of the denominator. That's what it means for the limit I want it to be zero, and that's the end of the proof. And I summarize. And I tell the method. You start with what you're trying to bound and add and subtract certain terms so that you have an upper bound on the thing that you're trying to bound using things you can control. Right? That's like what you do all the time analysis in calculus. And I think at this point I execute the rug pull, namely that this proof actually is not correct. And after I say it's not correct, I give some time, I think, so that you guys can figure out where the mistake is. And it's a very subtle mistake, actually. And that's why I did this in class. And why, how did I come up with this? I was trying to prove this, and then by myself, and I was like, oh. And then I realized it doesn't work. This is like the first thing you would do, but it doesn't work. And then I say, oh, of course you should be suspicious, because I told you that this is a consequence of the mean value theorem, and we didn't use the mean value theorem here. I just used the definitions. And then I made the point that, this is one of the messages of this class, in a sense. A lot of many students who are taking this class are not going to be professional mathematicians. So what's the point of all this? Like, why does it matter? It really doesn't, right? For many people, it doesn't matter, the specifics, the technicality, all that stuff. What does matter, though, is this experience. Math is scary, and it's hard, and it's often misused to hijack people's emotions, right? And so I said something like, oh, I'm a PhD, I know what I'm doing, and like, I don't second guess myself, all that stuff. And I write things down. I tell you this is a proof, but it's not, you see? So some amount of skepticism is good. Yeah, okay, I say the second and third summands are not the problem. The first one is the problem. The reason is that while the first summand I can bound by epsilon times h1 in norm, when you really think about it, even though I said fix h2, h2 is not fixed, right? That is to say, for any h2, sufficiently small, for any epsilon, there's a delta that possibly depends on h2. For any h1 less than the norm, then delta, this, that, and the other thing happens. So that limit is less than epsilon times h1 in norm. But you see, as h2 varies, maybe that delta varies too much, and you cannot control. And indeed, that's the first summand you cannot actually control. And I sort of made the analogy between triangular inequality and blackjack. And so, right, so in blackjack, you're at a certain number, and you sort of either say you hit me, and like you get another card, or no. But you want to get as close as possible to 21. So you want to increase your number, but there's a limit. And if you're not careful, you can go bust. And this is the main thing with triangular inequality. It's a very simple idea in a sense, but it takes a long time to master how to use. And I'm not trying to say that I'm a master, but I am relatively comfortable with using it. Let's put it that way. And I think I'm going to have to change the battery. Okay, let's keep going. I think I should pause here. deleted the wrong parts, and so I'm going to pause, change the battery, and go back. I mean, it's around like probably 7-8 minutes left. Okay. So I think here what I say is, as I'm trying to handle the horizontal perturbation, I say I'm going to use d1f at the wrong point. Okay. Okay, d1f at x1, x2, you see? It's not x1, x2 plus h2. Okay. Take the norm. Okay. Plus. Well, I need to make sure that I'm not adding new things. So now I need to put there f of x1, x2 plus h2. Yes. And I look at the remaining terms, f of x1, x2, and then the part coming from the vertical perturbation. And I say, okay, so the second part, it's fine. It's just a vertical perturbation. I can just control it by epsilon times h2 in norm. And I'm going to use the mean value theorem to control the first summand. And so for that, I'm going to define a certain auxiliary function just to make it clear to which variable I'm applying the mean value theorem. And I define phi of y1. So it's just going to be f of y1, x2 plus h2, minus d1f at x1, x2, which is a fixed bounded linear operator applied to y1. Now the point here is that, of course, this is a function that depends also on x2 and h2 and so on. I wrote it just so that it is clear what the variable is that I'm going to differentiate with respect to. And so phi prime of y1 is going to be, well, d1f at y1, x2 plus h2, just like with the standard single variable two-dimensional or one-dimensional partials. The variable that you're not differentiating with respect to, it just stays the same. And then I say, well, the second part is just one fixed bounded operator applied to the vector. And I'm differentiating that bounded operator with respect to the input, not x1, x2, but the vector y1, which means that by one of the exercises I gave you, it should be nothing but d1f at x1, x2. So that's a derivative of phi. This also means that phi is actually c1, because the derivative is a continuous function of y1, right? Because d1f is, it's a continuous function. So if the derivative of a function is continuous, then the function, that means by definition is c1, continuously differentiable. And then I say this summand I'm trying to bound really is nothing but phi of x1 plus h1 minus phi of x1. And now I write it out explicitly, just to verify. The point is that I'm going to apply the mean value theorem to phi, and what was the point, what was the hypothesis in the mean value theorem? I could only apply it to 2 points in the input space such that the line segment connecting them is completely within. But certainly, I can just look at x1 and x1 plus h and just shrink that small perturbation h1 to 0 by just like multiplying by a scalar that varies between 0 and 1. Okay, those two cancel out because of the linearity property of D1F. Okay, we're almost there. So now I write it again. P of x1, no, okay, I start with the thing that I'm trying to bound, okay. So this f of x1 plus h1, comma x2 plus h2 minus f of x1, comma x2 plus h2, plus d1f at x1, x2 applied to h1. So this was the first summand. I say, oh, this is equal to the norm of phi, okay, let me wait, norm of phi1, phi of x1 plus h1 minus phi of x1. And to this phi, I can apply the mean value theorem and bound it by sup of phi prime in norm times the difference between the inputs, which is just h1 in norm. So as t, real variable, varies between 0 and 1, I have the line segment that goes from x1 to x1 plus h1. So that's how I use the mean value theorem there. And you see phi prime in norm, or phi prime of x1 plus t, h1 in norm, technically that's an operator norm, times h1 in norm. And now I write explicitly this phi1 of x1 plus t times h1. And here I got confused with the where the line starts. So sup is like way below, but I'm going to correct it in a second. Yeah, I don't like these like chalk pens actually. I'm using them right now because it allows me to use the little bits of like chalk. I don't want to be wasteful as well, but yeah. That is that, I say. Okay, the second one I can control because of vertical derivatives existing. And so now I'm not going to write it again because I think I'm running out of time. That first box was what I was trying to bound. I'm going to bound it by that second box plus the third box. The second box I can control because of the continuity of D1F. Okay. Third box I can control because of D2F existing. So that's bounded by epsilon times H2. And this one is going to be bounded by epsilon because with continuity you just get epsilon. But I had a factor of h2, h1 there, as you see. Okay, and that's the end of the proof. Okay. And I think I say a couple more words here, but they are not super important as far as I can remember. I can't remember anything that I said that was worthwhile repeating here. And so apologies for the inconvenience, and I hope this recording is going to be helpful.